So I would like to welcome all of you to the ROCS lecture series, and a very warm welcome to our speaker today, Rebecca Jackson, who will speak to us about oceanic regime shifts and their impact on the Icelandic marine ecosystem. So Rebecca is a ROCS postdoc at the Globe Institute and the Geological Survey of Denmark and Greenland. She's a paleoceanographer and marine micropaleontologist, specialising in foraminifera. She uses the fossil foraminifera record from marine sediment cores to trace oceanic conditions back through time. We are very delighted to have her with us today. And but before we begin, just our usual few words of housekeeping. After Rebecca's talk, there will be time for discussions, which I would like if all of you participated in. You are very welcome to either speak up or post your questions in the chat. I would also like to remind you that the lecture is recorded, but not the discussions. The discussions will not be recorded. And the lecture will then be available at the ROCS website and on the lecture series Facebook page. So please feel free to turn your cameras off during the talk, but in the discussions, it will be really nice if we turn them on so we can all kind of be together. So now, Rebecca, I'm very happy to have you with us today. And so without further ado, I now give the virtual floor to you.
Great, thank you, Anders. I don't think I need to introduce anything else. That was fantastic. And thank you to everyone for joining today. I'm going to talk a little bit about the project that I have within the larger ROCS project. A little introduction, of course, to why it's important to understand oceanic regime shifts in the past and their impacts on marine ecosystems. A bit about how we can do that, and specifically in my project, what methods I'll be using, and of course, what material we're going to apply these methods to in order to answer these questions. Okay, the mouse doesn't work. Good start. So we've had a few talks in this lecture series already about the circulation system around Iceland, the modern circulation system. So I'll very briefly go over this again. Of course, the oceanic system around Iceland is intrinsically linked to that of the North Atlantic circulation. So whereby from the south, we have heat and salt advected in towards the south of Iceland, and cooler and fresher waters coming from the north via the East Greenland current, the East Iceland current. So really, in a sense, and maybe this is an interesting point for the future as well, that the waters around Iceland and the conditions that we find around Iceland may also become potentially increasingly linked to what's happening in the Arctic as well. And the configuration of these currents is modulated by the subpolar gyre put here, which in turn delineates the position of the polar front. This is dotted line here. And this is quite critical for a lot of the currents around Iceland, and in particular, the mixed layer depth. So the depth at which the water mixes rather, I should say. And the depth of this layer is really critical for controlling heat down into deeper waters, carbon cycling, the ocean geochemistry itself, and of course, productivity in the surface waters. So it's quite a variable and very interesting place to look at how all of these current systems come together. and how that might have been different in the past. We also have deeper waters coming in from the Nordic seas as well, and through the Denmark Strait. So there's a lot of things at play here that make this a really interesting place to study ocean circulation, and how what is happening in the wider area translates into conditions that we see around Iceland, which of course in turn affects the ecosystems, marine ecosystems that we find. But this is variable through time. So, for example, in the 20th century, there's an exceptional warming in the waters south of Iceland has overprinted this North Atlantic warming hole, and by hole we mean it's cold. And that's changed the ecosystem quite dramatically, actually, in that there's now mackerel as a viable resource found in the waters south of Iceland, for example, which hasn't been the case necessarily in the past. And if we look further back in time, this is very similar to the diagrams that I showed you earlier, but this is during marine isotope stage 5, and what is happening in the wider North Atlantic circulation system back through time. And through this is one interglacial, a very variable one admittedly, but this is one warm period. So this is how it looks in the modern. You can see this is a subpolar gyre here, and this advection of warm water north, and the Arctic front sits around here, so very close to the area that we're interested in. But even within this interglacial, there have been very different configurations, even where the subpolar gyre might not have been active or severely reduced. So reducing that northward transport of heat and bringing the polar front and the Arctic front here south of Iceland, in fact, leading to, of course, cooler sea surface temperatures in the area. So that leads me kind of to my research question. What characterises the Icelandic ocean and ecosystem impacts of global change? So how are these changes in the wider system characterised in Iceland? Is it always responding in the same magnitude, for example? And in particular, with regards to time, how long does it take for changes that we see in the wider ocean circulation, wider global temperatures, atmospheric temperatures even? How long does that take to make it into the area around Iceland, and what impact again does that have on the ecosystem? And so we're particularly interested, and this is of course coming back to when we think of what we might want to know, or what climate states we might want to try and predict in the future, is that we're trying to look at this and how this worked during past warm periods, for example, like the marine isotope stage 5 that I just showed you, as well as how this changes, and this is to do with leads and lags as well, how this changes across abrupt climate transitions, and how the oceanography and the ecosystems are changing. And of course, we're not at liberty to go back in time and measure water temperatures or productivity directly, which we were. So we have to take from these marine sediment records, and I'll come back to these in a moment. We have to look back through these for proxies, for ways we can try and infer water column structure, temperature, salinity, and this kind of thing. So one of the ways in which we do that, and one of the ways in particular that I will be doing that in the project, is using the fossil foraminifera record. So for the unacquainted, there might not be many here, I don't know. Foraminifera are single-cell protists that are distributed throughout the world's oceans, also in brackish waters. And they really are ubiquitous across water depths, different temperatures, and so on. And they're quite, maybe not as much as diatoms that Christina introduced to us last time, but they really are, by number, a huge part of the marine ecosystem. And these have two life modes, let's say. So we have planktonic foraminifera. There's some examples up here of some of the common species that we find. And these float freely in the water column, they're buoyant. And so they inhabit the surface or the subsurface of the water column. And then we have the benthic ones, and I've put some examples here. So these are foraminifera that sit at, or even below, actually, the sediment-water interface. So they primarily are related to what is happening deeper in the ocean, as opposed to these planktic foraminifera. And there's even two, let's say, types of foraminifera. So we have the ones that form calcium carbonate shells or tests, and that's most of these lovely looking ones here. And then we have agglutinated forms, which is possibly my favorite. It's like the ugly duckling somehow of the foraminifera world. This is an agglutinated foraminifera. So rather than building its own, producing its own calcite shell, it just produces a bit of cement, which then sticks together all the grains from the surface that it lives on. So it scavenges the grains that then form its tests. So these are particularly beautiful, I would say, but that's my own personal opinion. And the different species that we find, and there are many, of foraminifera, we know that they have different environmental preferences. So, for example, planktic foraminifera. Maybe it's a bit more nuanced than this, but in general, you can see here, this is a study of surface sediments around the world. So very top where these foraminifera have just landed when they secrete their shells. And in general, the species distribution, so there's different species here, and the proportion of all the species present, planktic species present, that you would expect them to represent, is how wide these are here. So you can see the different species are very, very clearly linked to sea surface temperatures around the world. So, and the blue here, and our polar species, we generally have neoglobal quadrina pachyderma as sometimes the only species, quite often the only species, but the very dominant one. And then we have a transition where we have different species making up more different percentages of the total assemblage, with a lot less of these polar species, obviously, at higher annual temperatures. Excuse me. So this is very nice, actually. I quite like this diagram because it shows quite clearly that Iceland is really very close to the zonation of these different species. So any shifts in temperature are probably going to move these species around Iceland. So this is also we're in the subpolar belt here in Iceland, but you can see, of course, we're very close to the polar front here, and also this transitional zone to the south of Iceland. Benthic foraminifera also have different environmental preferences. These are a little less well studied. I will put that out as a caveat. Because of course they live on the ocean floor. They're also, their distribution is also dependent on water depth, for example, current strength. And we sometimes have issues with the preservation if this is very, very deep water. These calcite shells often dissolve out, unfortunately. So it's a little bit more tricky with benthic foraminifera, but we do have some ideas of the distribution of different species. So that's a qualitative way of using fossil foraminifera that we find in the sediment to try and infer past oceanic conditions. But if we have enough of them, we can go a little bit further, and we can actually start to investigate the geochemistry of these calcite shells specifically. So these calcite shells that form in seawater, and they record the condition, the chemistry, sorry, of that seawater in which these shells were formed. So we can use a lot of the geochemistry within these fossilized shells to try and elucidate many different things. Paleothermometry has been a big one and is used, there's a lot of different ways to measure this. One of the more common ones, this is applicable for planktic and benthic foraminifera, only the calcite ones though, not the agglutinated ones, is that the magnesium-calcium ratio is temperature dependent. So calcite incorporates variable amounts of magnesium into the crystal structure, and this is very dependent on temperature. So you can see here, for example, this is some measurements on this species, amongst others, that there is a calibration, a curve between the magnesium-calcium ratio that you would expect to find in a given shell or a group of shells, and temperature. So this is very helpful because we have these different species-specific calibrations. We can actually draw a quantitative temperature, so a number rather than an inference of warmer or colder and so on. And if we couple that with stable oxygen isotopes, I think maybe quite a lot of people would have heard of these. This is also recording the oxygen isotope composition of the seawater in which they're formed. And this in turn is a function of temperature and global ice volume. So I don't know if anyone's familiar with this curve here. This is a stable oxygen isotope curve based on a stack of benthics. So many benthic stable isotope records all put together. And this is basically the heartbeat, let's say, of the climate in the past. So we are here in the current interglacial, the 1, and you can clearly see that as it gets colder and warmer, that's that marine isotope stage 5, again, that I showed some pictures of in the beginning, and you can clearly see that this number, or this this ratio, so I should say, follows the global climate. And if there are many records where this has been used as a correlative tool as well. And not only that, we can also use foraminifera for radiocarbon dating. So they're very useful. So we have it as a correlative tool. They can tell us something about temperature, salinity. And if we combine certain measurements, in particular stable isotopes and magnesium-calcium ratios, we can track backwards. So the unknown that we have is the seawater delta 18O signal. We cannot measure that. But if we combine, or we can't go back in time and measure that. So if we combine magnesium, calcium and stable oxygen isotopes, we can backtrack, calculate the seawater delta 18O, and from that in turn, we can also calculate salinity and see how that changed back through time. And there's a number of other trace metal ratios that are being used now. For example, barium calcium and cadmium calcium track brine formation and formation of deeper water masses. I might come back to this later on. And also boron isotopes have been used as a proxy for pH and ventilation of bottom waters as well. So that's the how. And of course, the what really depends on what sediment records we can retrieve. And we were very lucky to retrieve a lot. So last June, a few of the ROCS postdocs and investigators and partners sailed on the Arni Frederiksson for 2 weeks, leaving from Reykjavik. And the main mission of this cruise was to collect sediment cores to investigate the paleoecology and the paleoceanography in Icelandic waters. And this included collecting sediment cores for eDNA, as well as a multitude of other measurements that we carried out along the way, such as CTDs, water sampling for eDNA, and optical turbulence measurements. And despite a breakdown of the sub-bottom profiler, which is one of the main tools we use to decide where it is possible to get marine sediment cores, and some rather unfavorable weather, I would say, especially if you're thinking you want to put one of, a rather heavy gravity core over the side of a ship, we still managed to get to a lot of sites and get a lot of very promising material and sediment cores. And of course, what comes out really, we have to think about our research questions based on the material that we get. actually, because we know very little about these cores. So none of them were opened on board. This was to preserve the DNA and avoid any contamination from DNA from a fisheries vessel. So that's already maybe not the the cleanest place, let's say, if you're trying to preserve DNA. And we got 9 sediment, that number's not quite right. We got a lot of sediment cores, 9 of which were longer than 5 meters. So the gravity core that I showed in the last slide, this long metal tube, this is 6 meters long. We also extended it to 9 at one point to see if we could get even more sediment. And so the only thing we really had to go on before once we open these cores, you know, the sampling party starts, and we have to be very careful when we open them because of the DNA sampling. So in the beginning, the only information I could garner from these cores was from the core catcher. So at the bottom of the core, there's a device which stops the sediment falling out, essentially, as you pull it back out. And I was in there with my little spoon, taking some of that material to try and get an idea of how old these sediment cores were at the bottom. And I've put some of these dates on the map here. And what struck me straight away is that we have a lot of cores that seem to extend back into marine isotope stage 3, so beyond the last glacial maximum around 21,000 years ago. And this is really nice because, as I showed before on the maps with the ocean currents, this, if you imagine, this is where the Atlantic water comes north, it heads south, and then it heads up here again. And this is also where the polar front and the Arctic front lie sometimes. This is also kind of on the line where that Denmark Strait deeper, the overflow water, so this deeper current comes in, and the Iceland-Scotland overflow comes down here. So yeah, we picked these sites on purpose, obviously, but it gives a nice, if we look at these cores, it gives a nice transect. And so we started off by looking at station 8 up here, which was just over 6 meters long and with a date of 42,000 years at the bottom. Station 13, another 6 meter core that had a basal age of 37,000 years. And station 5, so a date of around 30,000 years. And sorry, I've just moved my picture. And so this transect of cores is really nice to try and track. We have a lot of quick changes since marine isotope stage 3, for example, going into a last glacial maximum, for example, so extreme cold period, and back into an interglacial. So the transect of those 3 cores, we hope to track these changes in the oceanography and the ecology across glacial interglacial transitions. And then also from that core, from that expedition, we have 2 very good candidates for higher resolution Holocene cores. So the Holocene is the last 12,000 years. And we have station 9 up here and station 4 down here. So if we can get this, these will be higher temporal resolution than the records that we have that are older but the same length. So here we can really look into very detailed, very high resolution changes back through time. So just to give you some insights into how these cores look. So this is station 8 here. This is the high resolution image and the radiograph. So an X-ray, basically, is what it is. And these are some of the elements that we find in the core. And very clearly, this struck me instantly, is that we have a really big calcium peak around here. And this is also followed by the strontium, and our iron and titanium seem to be doing something very, very different. And then another thing that I noticed was this zinc peak here. These are most likely artifacts, these peaks you see here. But this one struck me, and this is very clear that this is this dark layer here. But I'll come back to that one in a minute. And so I said this core was about 42,000 years at the bottom, but we also have an inkling that it might be slightly younger. We have another core from this site that the profile, the sediments themselves and the XRF profiles look identical. And we assumed that one of the cores was, well, they're from basically the same site. And the two core catcher dates were very off. So I was hoping to have an answer to this by now, but unfortunately this is still 42 or 25,000 years before present. But I'll come back to that in a minute. And so I started looking as well at the foraminifera from these records. And so this is this is station 8 again. And you can see the pictures here. And again, this calcium peak. And we're not short on planktonic foraminifera. So the number per gram of sediment is up to 5,000, which for micropaleontologists, I guess is kind of a lot. Maybe not if you look at diatoms, but for forams, there's a few, I'll put it that way. But the species that we find in station 8 are mostly, you can see here I've put the relative percent of the relative abundance of each species. They're largely green, and this green is this pachyderma, so that one polar species actually. But there is the appearance of some other species, but it's not so huge. Of course, this is only a few samples, but we seem to have some of the species, this Pterotilita quinqueloba. This is often found at the frontal positions, so maybe we are somewhere in between. Maybe the polar front is around this time, but I'm careful with my interpretations on so few data points so far. Benthic foraminifera are not as abundant, and this doesn't plot to 100 for the different species that we find. There's a few I'm not so sure about, and I'm also a little bit dubious about the counts. This is not, there wasn't so many for me to say this is representative of the entire benthic community, so we definitely need a new strategy where we can get enough benthics for a good community assemblage without counting 10,000 planktic forams. But you can see there is a bit of diversity in the record. And the planktic-benthic ratio, this is often used as almost not ventilation, but almost like a stratification or a mixing proxy. So we have periods when there is very cold surface waters, but the benthic species are relatively diverse. There is some interesting trends there, but I'm going to look at a lot more data before I discuss this in any more detail. So this is station 13, and we have an age on this of 38,000 years. Again, we're waiting for dates within the core itself rather than just the core catcher. Quite different sediments to station 8, but quite clearly, once again, we have this almost cyclical or pattern of calcium in this core, and it has the same with the strontium, and again the opposite with iron. And again, the zinc profile is relatively stable until we have this peak here that is not an artifact. And the foraminifera are, well, we see a lot of green here again, so a lot of those polar pachyderma species. But there's some other species in the benthic record, at least, that make up larger percentages of the assemblage. And these are particularly the yellow, the non-ionella species. This strikes me because it's often found at oceanic fronts, or often places where productivity is relatively sporadic. It's quite opportunistic, let's say. And just to compare these, and this is why I kind of made a big point about about the calcium record. So here's station 13 and station 8. I mentioned these zinc peaks on purpose. So this is the one in station 8 and oops, sorry. So first, this is the more obvious thing possibly. We have the same almost pattern of calcium. This same peaks, these very characteristic peaks in calcium. And one could argue that on a correlative basis. So again, we're waiting for the radiocarbon dates, and then this will be a lot clearer. But on a correlative basis, it appears that these layers here are perhaps these here. And I say this especially because of these zinc peaks that occur right after, these dark layers, very thin here, you can barely even see it. But these zinc peaks that occur after these carbonate peaks. And this is the record from North Grips, so the ice core record. And instead of the marine isotope numbers like we had before, these are Dansgaard-Oeschger events, so warm intervals that have a very distinctive pattern. They come on very quickly, it gets warm very, very quickly, and then it tails off to cooler conditions again. And it looks, or it could look, like these calcium peaks, which are not detrital. They are very, very likely a lot of foraminifera, basically. These seem to correlate almost, you could see, to some of the peaks in this record. But again, dating is going to help us see if this is the case. So these could represent intervals when there's a lot of warm water coming into the south of Iceland and a lot of primary production. And I mentioned these station 9 and station 4, so the more detailed Holocene records. I think station 4 is next on the list to open and sample for eDNA. And this is particularly interesting, especially station 4, because this is 7,000 years in 6 meters of sediment. This is really quite high resolution, and we can certainly find a lot of rapid changes in there, and they're particularly relevant, these Holocene cores, because we have Wes, I'm not sure if he's here, but he's another ROCS postdoc who is working on the lake records from Iceland. And there's a few candidates that from the lake records that cover the entire Holocene. And we can link the marine and the terrestrial chronologically with tephra. We'll be looking for tephra in both lake and the marine records, of course. But also in that we can see if changes on land, I mean in the last 2,000 years, that also includes, of course, the human part of the system. And if the ecosystems on land and in the ocean are changing coevally, if they're responding differently to climate, and how this all fits in together. So we have this, this is a really nice kind of holistic way to look at marine and terrestrial and ecosystems and climate and how this all fits together. So the next steps for the project are first to get the chronology tied down for these. So we'll be looking for tephra marker layers and of course more radiocarbon dating. Doing a lot more work on the forams and getting some of the geochemical analysis started, so the stable isotopes and the magnesium calcium, and also begin work on station 5. Unfortunately, I don't have the XRF data for station 5. The last section is getting measured today. Otherwise, I would be very interested to see, for example, if these carbonate peaks are here as well, and if we can track events around here. Anyway, but we'll see. I'm sure it will come right after the presentation, and I'll be like, I wish I could have shown that. Anyway, but we've been, of course, as we've been opening these cores, we've been sampling them for DNA at 5 centimeter resolution so far. I think I will go higher for the Holocene ones. So we already have over 350 samples in the pipeline for eDNA. So this is the ecology that we can't see in the sediment, but we can still measure. And one more wish list, let's say, is that there's an expedition in summer by some of my former colleagues from Germany, actually. And there's the possibility that we can, we wanted to go back to the Emian. And there's a possibility that we could do that with a longer core than we had on board the expedition last year. There was a lot of detailed sub-bottom profiling, so we have good ideas where or how far down we would have to get into the sediment to recover Emian sediments. So this is the marine isotope stage 5, so 120 onwards 1,000 years ago. And so it's a possibility that we might have some Emian records coming. And I'm also talking with Christina about some surface sediment samples around Iceland as well. So lots going on, lots of questions to answer. So please, if you know anyone who's interested in a bachelor's or master's project and likes mud, please send them my way. Also microscopes, they have to like microscopes, it's a prerequisite. But yeah, and so with that, I would like to say thank you, and here's some references. And I'm looking forward to answer any questions you may have. Thanks.